Our human eye is not very sensitive to brightness differences. However, we are very sensitive to color differences. If you have a mixed color source, red, green, blue, and white, and you suddenly apply a thermal management in each power supply separately, and one tends to be a bit hotter because maybe there's low airflow, and you start reducing the power of the one power, you change the color of the light. That's going to be very obvious.
Can you share a situation when you had this impossible engineering challenge, but your team had to come together and figure it out?
Yeah, together with one of my clients, I cannot release the name, but we were facing a challenge with one power supply in a power plant. And every 3 months, there were several, let's say 20, 30 power supplies in one application. And every 3 months, one was failing. We did not know why. So I had to fly over, and then we were spending there, in a hydro dam. Anyway, we put data loggers on it. We monitored the power line. Long story short, in the end of the day, we learned it was an interaction between the power transformer next to the generator and a pump or two pumps turning off at the same time while the power supply is operating. That created a surge on the power line, which was killing one ballast, and that ballast that got killed protected the others. Yeah, okay. That's completely out of spec. So now how do you address this? Because
how did you find out that was the problem?
Well, we found out later on that we had a jump and we saw some dips, and you hear some noises, and then you consult with the power plant power engineer, and it turned out this is like when you have a inductance, like any transformer has a inductance, and when you have a shutdown of a power consumer, the inductance, the energy that's in the inductance will continue to go, and it will drive the voltage up until it finds a place to discharge. And that discharge point was our power supply.
Oh, wow.
It's just like, say, when you have a thunderstorm, when you have a flash coming down, where will it go down? Normally the needle which stands up, so you purposely give it a place to discharge, which is then grounded in order not to set the house on fire. It's the same analog system here. You have to give that pulse a way to run without killing that pulse. So we developed a special product just to do exactly that.
Oh, okay, I see. And then everything stayed.
Then it was resolved, yes.
Wow.
But it took us several months to get there.
Wow.
And at the same time, we had a failure every 3 months. Because when it was synchronized, it happened.
Mm-hmm. So this is stuff that you can never anticipate when you're working with clients in the beginning. Can you share a little bit? I'm just so curious. How do you incorporate all of this into your business model? Do you guarantee that you're going to solve problems down the road, or
we cannot guarantee it. Nobody can.
Yeah.
I mean, that would be an overpromise to do.
Right.
But what I can promise is that we're not going to ignore it, and that we're going to pay attention to it, and that we'll assist with our customers to find a solution for it, and that we are dedicated to help, because we are in for the long term. But of course, also running a business, you cannot be a charity and pay for everybody else's problem. That's not going to work either.
Yeah.
I mean, let's be very realistic.
But I mean, I think the deal you make in the beginning is you might manufacture something, help them manufacture something, but down the road you're doing a totally different job, which is more like crisis management.
Well, if there is a crisis, but the point is, again, as explained earlier, there are always so many unknown parameters. Okay. Yeah. If you set up a clear spec and you have measures to make sure that the spec is kept, and you violate that spec knowingly, then of course this is sabotage. But
Yeah.
if there are things that not working in the application because they weren't considered in the beginning, well, then you need to cooperate openly, well, to make it work. And that actually, what I would say, this also is a difference between the short-term build-to-flip companies and those long-term companies that occupy a specific niche markets, because it takes years, decades to accumulate all these know-how.
Right. Right.
They're not given in the front.
Yeah.
Yeah.
And then you have these decades of experience that you can then.
We have some experience, of course, but we expect our customers also to build at least the experience.
Right.
And one of the challenges that you have in Asia, especially, is that there is a higher turnover rate in the human resources. And with the turnover of the human resource, a lot of knowledge is lost.
Right.
And that's, I would say, one of the fundamental difference to Japanese and Northern European companies, that the turnover rate of the know-how keeping engineers is much lower.
In Europe?
Europe and in Japan,
Oh,
compared to North America and Asia.
Oh, okay. Huh.
So that's why in our company, we operate with an cloud-based internal system. It's a server-based system where all the communication that we had related to projects is stored.
Okay.
Because you have to anticipate the effect that the lifetime of your products way exceeds the time that an employee resides in your company.
Yeah. Yeah.
So how to store the knowledge, how to make sure that you can absorb it, how to make sure that you're not losing this knowledge when somebody leaves the company. It's one of the key elements.
Yeah.
Knowledge management.
So can you go over thermal management? What is it, and why is it such a challenge for engineers?
Okay, so as every power supply is a converter, it's never perfectly converting all the energy. So some energy will be released in heat, but the heat is not evenly distributed in your power supply, but will be linked to specific components. Let's say a power transistor or an inductor or even a capacitor where there's a ripple current on it. It will create heat. Now, if the power supply is consigned in a space where there's no airflow, there's nothing, the heat will raise the temperature of that part until the equilibrium between the heat generated and the heat transmitted away is reached. This can be simulated. There are the thermal simulation programs, and when you design a device with an active cooling, like a fan, or like in your PC, you some have water cooling, you can simulate where this will go. And it's better to simulate that early, not later, because the heat on the components will fundamentally influence the lifetime of the components that are heating up. So there is a rule of a thumb way saying, like, when you have a capacitor, for every 10 degrees you go down, you double the lifetime.
Oh.
So for a rated life, let's say the rated temperature is 105 degrees and they give you 5,000 hours, you go to 95, it's 10,000. You go to 85, it's 20,000. You go to 75, it's 40,000. So now, it makes a huge difference whether you're at 77 or 87 or 97 degrees.
What is the compromise you have to make once you add the cooling in there? For example, the fan, and then it's got to be bigger, right?
A, it could be bigger, B, it could be noisier. So if I have, for instance, we talk about audio amplifiers, which also has a power supply inside. When you have a quiet cinema scene, you don't want to hear a fan, right?
Right.
But when you have a noisy hard rock concert, you won't care about the fan blowing. So the heat management process comes back to your application. If that power supply is somewhere in an electrical cabinet down in the basement of a factory, nobody would care. When this is in a concert hall, they will care.
Yeah.
So again, it's not a one-fits-all solution. You need to understand where it's being used, how it is done, what are the management, what is the things. And for lighting, for instance, our human eye is not very sensitive to brightness differences. We can absorb 15, 18, 20% brightness difference we don't see. However, we are very sensitive to color differences. So let's say if you have a mixed color source, red, green, blue, and white, and you suddenly apply a thermal management in each power supply separately, and one tends to be a bit hotter because maybe there's low airflow, and you start reducing the power of the one power, you change the light, the color of the light. Oh, that's going to be very obvious.
Yeah.
So again, how you manage it is very, very important.
Yeah.
And that's for the application. And then for the component location in the power supply or in the cooling method, or how much copper layers you put into the PCB to allow the heat to flow away from the components. These are design parameters engineers or power engineers deal with every day. It's very common.
Okay, so at Celinius, how hands-on are you guys in telling the engineers on the customer side what are the parameters that they should control? Are you doing this kind of consultant role, or are you just kind of presenting all the options and let them decide?
No. Normally we try to understand the target parameters of the applications first. And then, so we ask them, give me a typical scenario of where you're going to use it. Give me a typical load condition. And then we start from a typical design, and then we say, okay, now let's talk about the exceptional parameter that the system still has to do it. And then we'll ask them, okay, in this exceptional parameter, what kind of behavior can you accept and which ones cannot? Give you an example. If you're a DJ in a club and you are playing music and your amplifier is getting really hot because the crowd is dancing and those things. Okay, now the amplifier reaches the critical temperature level. You have to decide on how do we deal with it. Typical way is, whoom, shut down. No sound. Will ruin your
career.
Your career, yeah, right. So that might not be the proper management way to deal with overtemperature.
Right.
But that's the default way. The second way would be, okay, we slowly reduce the output and keep the temperature at a certain level. Maybe the crowd is a bit less loud, noisy, but at least they won't complain.
Yeah, I mean, I might have to play Elton John or something for a couple songs.
Yeah, like this could be also, but you make it a warning line that you know that you have to do this. That's my smarter way to manage the over temperature condition. Or you put another fan there and you turn this on to blow it down. When it's noisy, nobody will care. But that is your end product requirement. So first of all, you have to make the customer aware that there is such a need to address that.
So you would ask the customer, what is the preferred scenario for your industry and your customers?
Yeah.
And then you design to meet those needs.
Yeah, well, normally we don't start from scratch.
Right.
We tend to see, okay, tell me which product is already close to where you want to go, but show me what's not great with it. Okay. Then we pick up that, and then we verify where specs are, what additional parameters need to be specified. And when you do this, you give a very specific request to the manufacturer's engineer that can be understood, and not something fuzzy. I don't want my system to shut down when music is noisy. That's power supply engineer cannot work with.
Right.
But if you can say like, okay, I can accept that my output is reduced by up to 20% when the temperature is raised, but I don't want that to be abrupt. I want to have a curve that the reduction is happening over a time of 10 seconds. That an engineer can work with.
Okay.
So you have to be the translator between the
Yeah.
customers' market needs and the engineers on the ground.
Okay. So you have to strike a balance. Yeah.
Yeah.
Okay. Great. Thanks for that. We learned a lot today.
Great to be here with you, Michael.
Yeah. So see you in the next one.